Hi everyone. Um, so this is part two of a voltage divider PowerPoint. So the first one you should have completed or looked at was using the Colorado FET simulation software to establish the relationship between the resistances and the voltages in a voltage divider circuit. So this is moving on from this. It's a bit more theoretical. That was using the simulation software to carry out a virtual experiment, as it were. And so this stuff we're doing now is more the theoretical and how you would do calculations, etc. But feel free to use the software to try out any of these examples that I'm going to do, because it's top-notch software and it's really worthwhile using. Okay, let's go on. So just a wee quick reminder, this is kind of the thing we were doing in the previous PowerPoint. So this is a voltage divider circuit. So you've got two resistors in series, and basically the voltage from the power supply, in this case it's a battery, is split up or divided across each component, such that that's one of the rules for a series circuit, that the voltage from the supply equals, that would be V1 and that would be V2. And if that's a 12 volt battery, 12 volt power supply, then in this case, because the two resistors are the same value, then the voltage will just split up evenly. So your 12 volts splits up 6 volts and 6 volts. And that's because these two resistors have the same value. So each resistor gets the same share of the voltage. The voltage splits up equally in this case. You will get examples about that, but obviously the more complicated ones are where these numbers aren't just quite so simple as that. So this was the relationship that got defined in the previous PowerPoint. So basically what it shows is that if that's R1 and that's V1, that's R2 and that's V2, then the ratio of the resistors is the same as the ratio of the voltages. In other words, the voltage splits up in the same ratio as the resistor. So because these are the same, so therefore the voltages are the same. We're going to look at this relationship in a wee bit more detail. So here we've got another circuit, different this time because that R1 is now double the size of R2. So you can answer these questions when the numbers are simple like this. You can answer these by doing a kind of proportion calculation or a ratio calculation. So in this example, the ratio of the resistors is 2 parts to 1 part. So there's 3 parts in total. 2 parts of the voltage will be across R1 and 1 part will be across R2. Means the voltage splits up 2 to 1, and R1 would get double the share of the supply voltage. And you could probably work that out in your head. So that's going to be that V1 would be 8 volts and V2 would be 4 volts. Remembering that V1 and V2 have got to add up to the supply voltage. The other way you do this is because it's 2 parts and 1 part, then you would say that's 3 parts in total. Then this voltage here will get 1/3 of the 12 volts, which is your 4, and the V1 will get 2/3 of the 3 parts, if you know what I mean. Okay, so that's for nice easy numbers like this. And main thing you need to remember, especially for the stuff we're going to move on to for the electronics, that in a voltage divider circuit like this, that if you can remember that the larger value of the resistor or the largest resistance in the circuit will get a larger share of the voltage. That's kind of crucial for stuff we're going to do later on in electronics. So in the same sort of manner, this one got the same sort of circuit, but this time R1 is 3 times the value of R2, and so therefore V1 is going to be 3 times bigger than V1 is going to be 3 times bigger than V2. So it's a ratio of 3 to 1. So in other words, you've got 4 parts to play with, and the ratio will be 3 parts will be across that, and 1 part will be across V2. And so therefore, if we do it as a recalculation, V2 will get a quarter, one of the 4 parts of the supply voltage. So a quarter times 12 would give you 3 volts, and V1 would get 3/4 of the supply voltage, which gives you 9 volts. And as you would expect, that means that V1 is 3 times the value of V2. Okay, so that's kind of how you do it if you're just doing it by proportion or by ratios. But there is another more powerful equation that you can use to calculate V1 or V2 if the values, these are still quite easy values. R1 is 30, R2 is 20. So you could probably work that out in your head, but I'm just going to do it using this equation that you need to be able to use. It's called the voltage divider equation, and that's it there. Now, at first looking at it, you think, what is that about? But we'll go through a few of these and you'll see that it's quite straightforward. Now, this is as it appears in the relationship sheet, because it does it in terms of V2 and R2. I don't really know the reason. Somebody did explain it to me one time, but I can't remember why they don't just call it V1 and make that R1. Doesn't really matter. And it doesn't really matter which, whether it's V2 or V1 that you want to find, as long as if you want to find the voltage across that resistor, then that's your value, that's your resistor that goes on the top line. Okay, so in this case here, that's going to give us that R2 is 20 divided by the total resistance, which is 30 plus 20, and then that's times the supply voltage. And if we do that, that gives, excuse me, a value of 4.8 volts. So the voltage across R2 is V2, and it's 4.8 volts. Now, 2 ways you can go from here if you have to calculate V1. Well, it does say that in the question, to calculate V1. So the long-winded way is you go through the same calculation, but we'll call it V1 and R1. It's the same equation, doesn't really matter. So then you're going to do 30 divided by 50 times 12, which works out to be 7.2 volts. Now, clearly, you don't have to do that, because if you remember from the very first slide, or in fact the second slide, if the supply voltage is 12, that you know that plus that, the V1 and the V2 has got to add up to 12. So if that's 4.8, so you just take 4.8 away from 12, and that would give you the 7.2 volts as required. Okay, so this is stuff I mentioned a wee while ago, that the whole voltage divider circuit questions are deemed to be quite difficult for some people, or people find them quite hard. But if you can get a grasp of them just now, then it helps you with the sensing circuits that we're going to move on to in electronics. The basic thing about that is about the bigger the value of the resistance in a voltage divider circuit gets a bigger share of the voltage, and conversely the smaller value of resistance gets a smaller share of the voltage. So, understanding how these circuits operate is going to be much helpful later on. Now, we think about how they draw circuits can be slightly differently, or can be drawn slightly differently. So generally they're drawn, when we come on to the electronic stuff, which we're not quite there yet, next couple of weeks it's going to happen. Generally they draw them with the battery to the left and resistors are on their side, so they're kind of twisted round 90 degrees. I'm going to show you there's three circuits that are actually exactly the same, okay? But I'm just going to show you how they work out. So that would be your standard circuit that we've been dealing with up till now. So you've got a power supply, a battery, you've got 2 resistors, R1 and R2. So this is a voltage divider circuit, and we're monitoring the voltage across V1. So the first stage is sometimes you get the resistors on their side, like that. Now it's exactly the same circuit. You've still got your power supply, you've still got your 2 resistors, and we're still monitoring that. All we've done is switch that round anti-clockwise 90 degrees. But when it comes to electronics, they do this, which basically they have a top line here, which is deemed to be the plus 5 volts. And then you've got a ground line or an earth line, the 0 volts here. And all voltages, etc., are measured with respect to that 0 volts line. So this circuit here, where your R1 and your R2 is a voltage divider circuit. It's exactly the same as these two circuits here. It's just drawn in a kind of different way, that you don't have any, line or indication that this is a battery or a power supply. You just see that's your plus 5 volt line, it's called, and that's your 0 volt line. And this is your output voltage, because the output voltage is always measured across the bottom resistor, in this case, with respect to 0 volts. So using this kind of new version of our circuit, we're going to calculate the output voltage in this question. So we're going to use, all right, there we go, sorry I forgot about that bit. In this type of question, output voltage is across the bottom resistor, and it's measured with respect to 0 volts, but we're going to use our newfound voltage divider equation, which is V2 equals R2 over the total resistance times the supply voltage. Okay, so in this case, so we want to find the output voltage, which is the voltage across the 30 ohms. So that is going to be your R2. Doesn't really matter which one's R1 and which one's R2. You could call this R1 and then make the equation V1 equals R1 over R1 plus 2. As long as the resistance or the voltage that you want to calculate is across that resistor, then that's the resistor that goes on the top line. So it's 30 divided by the total resistance, which is 30 plus 120, multiplied by 5, which, if my maths is correct, gives you 1 volt. So you could, if you were asked to find the voltage across the 120 ohm, you aren't in this question, but you could be, then hopefully you can figure out, well, if that's 1 volt across there, then that must be 4 volts, and because it's got to add up to 5 volts in this case. So therefore, the voltage across the 120 ohms is 4 volts. Now I've got a wee question here, which I want you to kind of have a think about, and then I'll give you the answer in a second. So the question is, so in this circuit here, we've got 120 ohm and a 30 ohm resistor in a voltage divider. Now, what would happen to the output voltage if we replaced the 120 ohm resistor with one of a greater value? Now, I've not actually given any numbers, so you can't do a calculation. Suppose you could make up a number and do a calculation if you really had to, but this is where you have to get a kind of grasp of the voltage dividers, and then you'll be able to answer this type of question really easily. So think about it. So we're making that a larger value of resistor. How is that going to influence what happens to the output voltage? So I'm not going to give you very long to think about that. Hopefully you're giving it a wee think about it in your head. The way to look at it is to do with the share of the voltage. Remember, way back a couple of slides ago, I told you that the larger the resistance, the more share of the voltage it gets. So in this case, if we're making this resistor a larger value, it's going to get a larger share of the voltage. Now, how is that going to affect V out? Well, V out has to decrease, because the V out plus that voltage, which we're not measuring or looking at, just thinking about it, has to add up to 5 volts. So if that voltage resistance is getting bigger, so that voltage is going to get bigger, so that voltage across here must decrease. If you don't quite get that, just go back over this page, reread my answer here. It just basically says that the top resistor has got a greater value, then it's going to get a bigger share, a larger share of the supply voltage, and therefore this must get a smaller share, so the output voltage would decrease. Fingers crossed you get that one okay. Okay, another example, same sort of idea. Want to work out V out, just going to rattle through this because hopefully you're getting it by now. So it's 14 over 14 plus 36 times 5. So that gives us that the voltage across that resistor is 1.4 volts, and therefore the voltage across the 36 ohms must be 3.6, because the 1.4 and the 3.6 have got to add up to the 5 volts. Now this is a similar question to asked in the previous slide. This one is actually a lot easier because it's asking about the output voltage directly, and we're changing the value of that resistor. So if we make the 14 ohm resistor here a greater value, hold on, I need to think about this. Okay, so if we're making the 14 ohm a greater value, then the bottom resistor has got a greater value, so therefore it's going to get a greater share of the supply voltage, and so therefore the output voltage would increase. We don't even need to think about the top resistor in this case, or the top voltage, because we can just answer it based on what's happening here. Incidentally, the 36 ohm resistor would get a smaller share of the voltage, even though that value, that resistor is not changing its value. Because this has got a bigger share of the voltage, then this must have a smaller share, because remember the voltage across each one has got to add up to 5 volts. So if that's getting a bigger voltage, then that voltage there must be a smaller value. Okay, last bit, I'm trying to show you like a super complicated question that you might be asked. So here we have voltage divider circuit. Instead of working out what V is, we're missing a value for the resistor. So the question is, calculate the value of the missing resistor R. Okay, so let's start off doing it with this equation here, because that's what we've been doing. But this time we know what V2 is, we know the voltage across that resistor. So if I substitute in the numbers, it kind of looks a bit weird. So we're substituting that the voltage is 2.2 is R divided by R plus 46 times 5. So I've substituted all the numbers I have. Okay, so then it gets a bit complicated, because we're going to turn it into like cross multiplication. So I've just said 2.2 over 1 just because we're going to cross multiply. Now R over R plus 46 times 5 just means 5R over R plus 46. So we're now going to cross multiply like this, remembering, well, 5R, I'm going to do that cross multiplication first. So that gives us that 5R equals 2.2, remember in the brackets, times R plus 46. Multiply out the brackets, gives us 5R equals 2.2R plus 101.2. Hope you're sticking with me. This is quite a wee tricky bit, kind of difficult. Therefore, take the 2.2R over to that side of the equation. It becomes minus 2.2R equals 101.2. So therefore, 5R take away 2.2R is 2.8R. So then we've got simplified it almost right to the end, and that gives us that the answer is 36.1. Now I know you're thinking, wow, I hope I don't get anything like that in any exam I've got to do. But the automatic thing when you see something like this is perhaps to use that equation. But there's an easier method, a much easier method to do this equation. And that would be using the equation that we've done right at the start, that we kind of derived from the experiment stuff, that R1 over R2 equals V1 over V2. Now, what it depends on is recognizing something. So we know this voltage is 2.2. And if this was the way it was given in the question, there's something you need to figure out yourself. And that is, okay, what's the voltage across the 46 ohm? Well, if you can figure out that's 5 volts, that's 2.2, then you can probably tell me right now what the voltage across there would be. And then that means using this equation, we've only got the one unknown. So we'll start filling in the numbers. So there you go. 2.2 away from 5 gives you 2.8. And so that 2.8 volts goes into the bottom of the voltage side there. So 2.2 divided by 2.8 equals our unknown R divided by 46. So we've got a cross multiplication again. Remember, top tip, the unknown thing, do that multiplication first. So it's going to be 2.8 R equals 2.2 times 46, which is going to bring us down to this line here. So it's exactly the same. And then, funnily enough, we get the same answer. So just when you do a question like this, look at all the options. Going through this one, I mean, obviously I've shown you every single stage and it makes it look really complicated. But this is a far simpler method. If you think about the question, take your time, don't just rush in and, figure it out. Okay, so as usual, there'll be a whole stack of questions for you to do on this stuff, and there'll be an assignment quiz on Thursday. So good luck again, and remember the live lessons that we've got on the go on Mondays and Tuesdays, depending on what class you're in, and best of luck.